right, welcome everyone to our Friday Transportation Seminar in our slightly different location. I'm Professor Jennifer Dill. I'm Director of TREC, the Transportation Research and Education Center here at Portland State University, and I welcome all of you to today's seminar. We're very happy to have with us Dr. Alex Bogazzi, who most importantly for this audience and context is an alum of Portland State University, having gotten his PhD here just a few years ago. But perhaps more importantly for him now is that he is an assistant professor at University of British Columbia in the Department of Civil Engineering with a cross appointment in urban planning or whatever.
Community and regional
planning.
Totally different.
So I think that reflects the interdisciplinary nature of his work, which was clearly grounded here at Portland State University. We're going to claim a lot of credit for Alex.
Yeah.
So we're happy to have him back to give his talk today about bicycles. And I'm going to save this announcement for the end, right? Okay, take it away.
Okay.
Thank you.
All set? Great. Oh yeah, thank you. Excellent. Thank you, Jennifer, and thank you everyone for being here, and welcome to the people online as well, the internetverse. It's exciting to be here. The cross appointment definitely is a result of my education at Portland State. I don't think there's many other civil engineering programs I could have gone through and ended up with a joint appointment. It's a really a nice aspect of the program here that I valued a lot when I came through, and hopefully those of you who are still involved in it are having the same positive experience about kind of interdisciplinary education. And this is definitely interdisciplinary, what I'm going to be talking about today. So finished my PhD in 2014, finally left in 2015 from Portland State, and I was looking at cyclist uptake of air pollution. And with Dr. Physiology as my supervisor, and in that we looked quite a bit at cycling physics, because the amount of energy you expend when you're cycling it determines how much you breathe, which in turn determines how much air pollution you inhale. It's one of the bigger factors in terms of cyclist uptake of air pollution. But while I was doing that, I got more and more interested in the relationship between energy expenditure and travel behavior. And so basically what I'm going to be talking about today is a lot of what I've been working on over the past about 3 to 4 years up at University of British Columbia, where I went after my degree here. So, when I got up there, we put together a research group to look at a number of issues. We did a little branding. My first master's student came up with a little logo there where the E and the A looks like a bicycle, which I liked a lot. So the Research on Active Transportation group, it's fairly vague title, but one of the kind of unique aspects of it is that we're trying to look at how, at the active part of active transportation in detail. So look at how cycling physics and human physiology actually influence active travel behavior. And to motivate that topic a little bit, yesterday I pulled up a local example. This was the first try, but I like the 3 options that Google Maps gave me. So say I moved out to the east side of Tabor. I wanted something closer in, but you know how the market is. So I ended up on the far side of Tabor with my house on Clay Street there, which is a random dot that I put on Google Maps. And I want to go to Porque No because it's delicious, get some tacos. And so Google Maps offers me 3 routes here. And so I can go kind of the closest to the Crow's line, a little bit over the south side of Tabor. I can go a little bit further out of my way to go along Division Street, higher traffic, but much flatter route. Doesn't involve the same hill over the mountain there. Or I can go farther away down into the neighborhood street and get a lot lower traffic route, but the longer route. And so, of course, there's a fair bit of research. A lot of it was done here, looking at cyclist route choices and showing that the one we most want to take is going to depend on our preferences, how comfortable we are going up and over hills, being exposed to the amount of traffic that's on Division, or taking a longer trip. But it's also, but what we're trying to add into this picture is that it also depends on how I personally feel about energy expenditure, but also the equipment that's available to me. So if I'm going to take this trip on my fairly well-maintained city bike, going up and over Tabor looks quite different than if I'm planning on taking a bike share bike, for example. Not knocking Bikey Town, but I imagine if you have the option between that and a personally owned bicycle, you're probably going to be much more comfortable on your personal bicycle. On the flip side of it, if you had, say, an e-bike available to you, again, these three route options are going to look a little bit different, right? So those, the attractiveness of those routes are going to depend on, obviously, the route characteristics, your personal characteristics in terms of how much exercise you feel like getting, but then also it's going to be mediated by the equipment that is available to you, right? And then since the equipment influences the attractiveness of the routes, that all kind of scales up into mode choices, right? And so if none of these three routes are attractive enough, I'm not going to cycle at all, and I'm going to take the bus, or maybe I'll walk or drive or something like that, right? So that's the motivation. Basically, the majority of the research on walking and cycling activity and active transportation outcomes kind of looks at how environmental and traveler characteristics influences walking and cycling activity, both the frequency and the intensity of it, and then connects those to traveler-related outcomes, things like health benefits and whatnot. And what we're trying to add in is more of the effects. I shouldn't be pointing at the screen, I forgot. More of the effects of energy and speed, how that influences walking and cycling activity, how equipment influence those, and add in a unique part of the traveler characteristics, which is our personal energy expender preferences and capabilities. And we think that this has a lot of potential applications in the transportation field related to how we estimate, how we develop our travel demand models, routing and network design, simulation and operation models. Bicycle microsimulation is increasingly common. And of course, it's important to understand bicycle dynamics. We need to understand this energy speed trade-off that cyclists have. New mobility policies in terms of, you guys now have the e-scooters on the streets. We don't have them yet in Portland, but there's a big push right now. And of course, health and safety assessments, because the amount of energy we're expending determines how much physical activity we're getting, right? I think there's a lot of potential for a more detailed understanding of how energy feeds into the walking and cycling picture. So that's what we've been working on. So a little bit of maths, but not a crazy amount coming up here. So in order to do that, in order to bring energy into our transportation analysis tools, first we have to be able to estimate energy. So there's quite a bit of research from sports science, kinesiology, sports medicine, focusing on sports cyclists that we can draw from. And this is a commonly used power equation. It's fairly straightforward. It has four components. There's kinetic energy, which means your acceleration or speed, your potential energy, basically going up hills, and then you have two types of resistances that you have to come. There's overcome. There's rolling resistance, which is basically your tires, and there's aerodynamic resistance, which is basically the wind. Okay, so you have two kinds of resistances and two kinds of energy, and that's all embodied in this equation. And like I said, there's a large body of research that exists for calculating this for racing and sports cyclists. So what do we need to apply this to utilitarian or traveling cyclists? Well, there's three key physical attributes that we need to estimate for cyclists. So there's mass that comes up a couple times in the equation. We would expect that to be different for most utilitarian cyclists. For example, the bike share bikes are going to be quite a bit heavier than a racing bike. There's a rolling resistance parameter that relates to your tires. A lot of utilitarian cyclists are going to have wider tires, lower inflation tires, things like that. And then your drag parameter. So that again reflects the wind resistance. So that has to do with the position, your position on the bike, if you're leaned over in the drops position, or if you're sitting upright, the clothing that you're wearing, the amount of if you have panniers, the baggage you have, things like that, right? So these all needed to be estimated for utilitarian traveling cyclists. we need to get a good estimate of the speed, and we need to have a good estimate of the road grade. So over the past 3 years, we've actually been spending quite a lot of time getting better estimates of these for everyday cyclists. So I'm going to talk about that over the next series of slides here. So the physical attributes of real-world urban cyclists was kind of the first thing we undertook, and I've got a bunch of pictures there showing the type of bicycles that have not really existed in the sports medicine literature because they weren't of interest to sports scientists for the most part. So we wanted to measure them for cyclists on the street. So the first thing we need to do was to come up with a method to measure resistance parameters for everyday cyclists. So here the issue was, so there's a number of methods to measure resistance parameters, and they vary in precision and accuracy, and they vary in complexity. And in general, the ones that are most accurate and precise also require the most cooperation of the cyclist, essentially. So there's you can instrument the bicycle, you can do long tests, but the idea was we wanted to go out and do an INTERCEPT study where we were getting real-world cyclists, and the more onerous it was for the participants, the less likely they were to participate, and the less representative of the sample we were going to get of everyday casual cyclists, right? So we figured most people on a trip aren't going to want to stop so that we can put sensors on their bike and then do a 30-minute test. So what we did was we build on a method called a coast down test, where you get a vehicle up to speed and then you let it just decelerate slowly, and you can measure its position or velocity over time and then extract the resistance parameters from that. We had to do some extra work because this was basically done ignoring wind conditions because it was done with cars where wind was not as big of a factor as it is for cyclists, or it was done in an indoor environment. So we built on that method. The same graduate student who came up with a cool logo at the beginning also came up with this second order differential equation to solve it. He was very proud of it, so I like to put it on the slide for him. And basically, so we went through a validation process where we did repeated tests on the same bicycle over and over with this test. And basically what we ended up doing is putting a lot more sensors. So typically for bicycle coast down tests, you do it with 3 sensors. We did it with 10 sensors to kind of overcome the additional variance from the wind and the grade. We had a high resolution anemometer. We came up with similar precision to past indoor methods. So we felt pretty good about this as a way to measure resistance parameters for real world cyclists. And then we went out and did it in an INTERCEPT study. So we went to 9 locations in a variety of contexts around Vancouver. This was in summer 2016. 18 weekdays in the noon to early evening period. And we went out on, like I said, different types of facilities, and we conducted this test. You need 100 meters of fairly flat terrain, although we still had to do some detailed grade measurements down to the centimeter because even small grade differences will affect the test results. And then we also did conducted a questionnaire, and then we measured attributes of the bike like the mass, the tire pressure, things like that. Let's see. We got 648 people to at least stop and talk with us and sign the consent form. 625 completed questionnaires, and a few of those didn't end up taking the test, and I'll show you that in a second. And the demographics compared pretty well to Metro Vancouver cyclists, where we saw more men than women and a dominance of people in their 20s, which was consistent with the household travel survey. I'll show a more detailed comparison a little bit later on. We were actually able to estimate resistance parameters for 557 of the cyclists. Basically, if we didn't get a good enough fit from our coast down test, we threw out the data, and basically, we think a lot of that times that was, if someone taps a brake, for example, you're going to get a bad reading because it's supposed to be just resistance from drag and rolling resistance. And what we found is, as we expected, we saw a much wider range and higher values of resistance parameters than in the existing literature, which was focused on sports cyclists, right? So your everyday cyclists that are out there are riding bicycles that provide a lot more resistance than what you would get if you use parameters from sports medicine research. And that's to be expected, like I said, but this is going to lead to an underestimation of energy and an underestimation of actually physical activity if we don't account for that. Here we've broken out, we have masses. As expected, women overall had lower body mass, but the bicycles themselves, women's bikes were actually slightly heavier than men's bikes, although not statistically significantly different, and there was no gender-based differences in either of the resistance parameters between men and women. But we looked at a number of factors, and as you'd expect with bicycles, a lot of the physical attributes of the bicycles interrelate, and it's all about what you would expect. Lower tire pressure, less rolling resistance, higher tire width, more rolling resistance, and a lot of these are indirect associations. So you saw less tire pressure, you also saw lower aerodynamic drag. That's not because they cause each other, but it's an indirect association through bicycle type. So road bikes tend to have more of a crouch position, which leads to less drag, but they also have narrower tires. So there's a lot of correlations in here. Larger mass, older cyclists also tended to have more aerodynamic resistance as expected. So what we're interested in, so in general, higher resistance parameters for less sport-oriented cyclists and bicycles. But what we also wanted to know is how do these relate to people's preferences and to their cycling habits? But because there's so many correlations amongst these attributes, we decided to do something called cluster analysis. And so we grouped these physical characteristics of the bicycles into typologies. We tried a number of different clusters, and we ended up with 3 as kind of the best fit clustering. And we labeled them mountain, road, and hybrid based on the characteristics of those clusters. Right? So we had 3 clusters. One was predominantly wide tires, flat handlebars, upright position, fairly low pressure tires, etc. On the opposite end, you had the road cluster, which was narrow tires, high pressure, a lot of drop bars, lighter, etc. And then hybrid is in between them. And we created those clusters just based on the observable characteristics of the bicycles. So what you would see if you just stood and looked at a bicycle. And then we saw the resistance parameters and mass characteristics you'd expect. So road bikes were the lightest, mountain bikes were the heaviest. But then connecting that to self-reported cycling frequency of the cyclists, we saw in general the types of associations that might be kind of called a typical stereotype of cyclists. So mountain, hybrid, and road cyclists in that order were increasingly and statistically significantly more likely to cycle year-round, road faster, self-reported speed, and I'll come back to that, engage in more weekly physical activity, engage in more commute cycling, and more likely to be in the strong and fearless category than the interested but concerned category, using an approach of 2 people in this room. So we asked them the same questions that Nathan McNeil and Jennifer Dill did in a previous study, so we could put them in that typology. But so in some ways, this kind of supports what might be a casual stereotype of the way cyclists look and their cycling habits. However, this is just referring to the differences of means within those clusters, and they were significantly different. However, the distributions within all of those clusters were really wide, and I think that's best represented actually in the cyclist typology results. So this is the distribution where you have no way, no how. There was a few people based on the way they answer the questions that were no way, no how. It wasn't very many, and my guess is a lot of these were tourists on the bike share bikes on the seawall. But there were a few no way, no how cyclists cycling. So it is interested but concerned, confident, enthused, and then the strong and fearless category. Okay, so yes, there are differences there, and they are significant, but there's a whole lot of strong and fearless people riding mountain-style bikes around the city, and there's a whole lot of people riding road bikes that would be interested and concerned, and even I think 2 that were no way, no how. Right. So so in some ways, yes, the averages tend to trend in the directions we might expect, but it actually has very poor predictive power. And In our next step, when we go out and we get GPS data from smartphone studies, we tried to use just the questionnaire data to predict their physical attributes. And I had a student working on this for quite some time, and basically it had we ended up not using it because it had very poor predictive power. So basically, trying to predict cyclists' physical attributes from just the responses to a questionnaire about how they like to ride is not a very strongly predictive association. Okay, so I don't know. It's a kind of a nuanced outcome, but the association is the direction you'd expect, but you certainly wouldn't assume everyone on a mountain bike is not confident cyclist. I'll leave it there. We could talk more later if we want. And then one more aspect of this is we saw people that were cycling on lighter, better cycling equipment. They self-reported tend to cycle more year-round and more frequently. But we don't at all know this is just an association. We do not at all know the causal direction there. My guess is that there's a bit of two-way causality, but I think it'd be really interesting to do some sort of an intervention or a longitudinal study to see can cycling equipment be an intervention strategy? If you give people better cycling equipment, does that actually change their behavior? Or vice versa, when people start cycling more, do they just go and buy better equipment? So we don't know that. We do know that there's an association, but we don't know the causal directions. We don't know how effective it would be as an intervention strategy. But I think it's really interesting, and that's definitely a next step. Another thing we did with the questionnaire data in the survey is we wanted to validate that the idea or support the idea that cyclists are thinking about energy considerations in their routing behavior, because that's the next step that we undertook. So we wanted to at least ask people if they were thinking about this. And so we did a structural equation model, which is illustrated here with another PSU alum, Dr. Gerke, who's somewhere in the world, somewhere in America right now. We looked at cyclists' consideration of safety, energy, and air quality in their routing decisions. And interestingly, we saw a significant negative association between cyclists who were focused on safety considerations versus cyclists who are focused on energy considerations, which suggests, again, kind of which kind of goes along with the more strong and fearless people in the more efficient kind of exercise cycling category. So there was a group of cyclists more focused on energy expenditure, and a different group of cyclists more focused on safety. The cyclists who are more focused on energy tended to cycle more for recreational purposes and get more physical activity, as you would expect. And they also were more likely to be thinking about air quality as well. So these might be more health-conscious cyclists versus more safety-concerned cyclists. But it did support the hypothesis we had that energy is going to be a big predictor of route choices. A couple other things we've been doing with the parameters, now that we have them, is using them, kind of going back to the dissertation research, using them for pollution inhalation modeling. This was a study looking at the optimal speed to cycle to inhale the least pollution per mile ridden. And then you see bands there, because we're using the statistical distributions of the physical parameters to say, because the heavier the bike is, the slower you should go if you want to minimize your air pollution inhalation, basically. And then more on the traffic engineering side, again, there's a distribution. This was looking at signal timing, so the clearance interval needed to get cyclists through a signal safely. So the cycling speed is going to depend on the resistance of their bicycle. And so again, here you can take a probabilistic approach to infrastructure design, where you say, well, we want to make sure the 85th percentile cyclists can get through the intersection in a certain amount of time. And we can use those resistance parameters to do speed modeling based on typical power levels while cycling. So we're using them for other purposes, but here in this talk, I wanted to focus more on the behavior side. So we worked on the energy estimation methods. The next was to get the GPS data that we need for speed and energy analysis to look at the relationship between routing behavior and energy expenditure. So for this one, we implemented a smartphone-based GPS data collection. I did a little bit of app programming, smartphone app programming when I was here at Portland State University. And at least from my perspective, creating a smartphone app is a nightmare. It's like one of the worst experiences. So I didn't want to do that. So we were looking for an off-the-shelf app we could use for this because maintaining compatibility with all the different smartphones out there is a real challenge. And we didn't want to limit it to a certain operating system. For this type of detailed analysis, we needed high resolution 1-second GPS data logging. And most of the smartphone apps don't do that because they're more interested in more aggregate characteristics, not this level of detail. We wanted to pair it with a heart rate monitor, so we needed an ability to do that. And we also wanted to minimize respondent burden, so we wanted to be able to get data from our participants directly through the app. So we looked at, I think, 14 different apps in detail. And there was one, actually, a local one, Ride with GPS, that worked well for this purpose. So we had participants use the Ride with GPS app to log their trips, and then they became friends with us, and then they could just share their data directly through that. They could log it 1 second, and if they wanted, so the heart rate piece was optional. But if they wanted to participate, we would send them one of these heart rate monitors. They're fairly inexpensive, about $90 Canadian, but with some early testing, they performed well. And they're worn on the armband, or on the forearm, so it's not as much of a burden as something that's worn around the chest, for example. You got to take off your shirt to put it on. Oh yeah, so as incentives, and this was fun, we made up some custom branded hats and socks. So if you were willing to participate with the heart rate monitor, then you can get some free hats and socks. What I learned here is that people want socks. And so I've got a lot of blue hats. And we had to reorder socks twice. I didn't bring them, I should have. I would have had to pay import duties though, I think, to bring it, so I didn't want to declare them at the border. Yeah, exactly. Yeah, yeah. So print up more socks. But those are actually pretty popular. So that was a fun incentive, and it was not that expensive if you order them in bulk. But just to warn you right now, so we haven't gotten to the heart rate data basically. So you're not going to see heart rate results. But we did getting a little clippage there of the slides. But we had about 250 people that filled out the questionnaire, but we only ended up getting usable GPS data from 150 of them, from 12 municipalities all around Metro Vancouver. So we had good geographic distribution. Got about 15,000 kilometers of data from 2,300 trips, and about 8% of them were e-bike trips. And we had a representative speed distribution, so we felt pretty confident about that. Now, oh yeah, sample characteristics. So we compared it both to the INTERCEPT survey from the year before and the household travel survey, and we had pretty good results. We did not get many youth, which was expected. So we didn't get the youth cycling, and we had, but we did get more in the older categories, and the income distribution was representative, and the gender distribution was similar to the Metro Vancouver cyclists as well. Okay, so data cleaning and processing. So this is where we got really sidetracked. So we had the lat long data from the GPS, and we looked at the existing cycling GPS studies and implemented what looked to be the most common approaches to get speed, grade, and acceleration from those data. And this is a summary of what that is, and I'm not going to go through it in detail, but because most of these hadn't really been looked at in detail, we looked at how sensitive our energy estimates were to some of these inputs. And it turns out they were very sensitive, especially to the grade data. So highlighted in red here are the three that we were most concerned about in terms of our results were really sensitive to them, and we didn't have good evidence in the literature that these were actually the best methods. They were just kind of what was being used without a lot of validation. So one is how do you identify? So people are recording data on a smartphone. You don't know exactly when the trip started and exactly when the trip ended. So how do you remove the activities or the stops? Remove that and isolate just the data from when people are traveling. Getting grade data, usually it's taken from a digital elevation model, which is basically a big grid overlaid on the Earth where you have an elevation point for every grid cell. That turns out to be quite problematic. And then how do you smooth the data? Because inevitably there are errors in it. So given how sensitive energy estimates are to these factors, we decided before we can go too much further, we needed to dig in detail. And actually, we're still working on quite a bit of that. These are the latest results from a student looking at more than a dozen different methods of separating travel from activity data in GPS trajectories. And we got a small validation data set. Green is good, basically. And then we have false positives, false negatives, and then omitted. And so you see a wide variation in performance. A lot of these methods were providing actually very poor prediction of what is a travel point from what is an activity point. So that's one of the ones we're working on. We're doing the same thing with map matching algorithms, which is where you take the GPS data and snap it onto the link, the street network. And then also looking at filtering and smoothing. So we've got some validation data and we're still kind of going through this, but so I don't have final results on the GPS, but we hope to be coming out with that pretty soon. And then everything else I'm going to say from that GPS data was using kind of these ad hoc methods. The grade one was one of the biggest problems. And here I've pulled out, so the Burrard Bridge is a critical link in Vancouver. It's kind of like the Hawthorne Bridge before the Chillicum Crossing was constructed. Like it was a whole area of the city getting to the downtown core. So a lot of people use this link, and so it was really a critical link for looking at energy expenditure. And then again, if we want to try to look at how energy influences route choice, we need to get good estimates of energy. And so these are, let's see, about a dozen different sources of grade data for the Burrard Bridge. And then any civil engineers? Okay, so you guys went out there with stadia and leveling rods and things like that. So we went out there with stadia and leveling rods, and we had them actually ground survey the bridge surface all the way across. We did that actually for 9 bridges around Vancouver. So they actually measured the elevation profile, and then we got a whole bunch of different data sources. And the only one that accurately represented the bridge surface was actually going all the way to LiDAR cloud point data and applying an algorithm which basically extracts the bridge surface from the LiDAR cloud point data, which is actually pretty computationally intensive process. All these other ones come from the digital elevation models, which tend to follow the ground surface, right? So if you're extracting road grades on a street network from a digital elevation model, any elevated structure is going to be way off. And then when we use these different grade estimates to generate energy estimates for cyclists across the bridge, we are 2, 3, 4, 5 times off in terms of the amount of energy expended to cross the bridge, right? Because it takes a lot more energy to cycle this bridge than it does this to cycle across it, right? So this ended up being fairly important, although there are only 30-something elevated structures within the municipality of Vancouver. It ends up being pretty important because these are critical links, right? We tend to focus bike infrastructure on bridges for a reason. These are important links in the network. So we ended up, this one actually, so this is just coming out, accepted yesterday, actually. So if you're going to be doing analysis using cycling GPS data, OpenStreetMaps has a flag for elevated links, which is really convenient. So on non-elevated links, using the highest resolution digital elevation model available is a pretty good approach. You have to interpolate, but it's a pretty good approach. For elevated links, if you want to be confident about your grades, you really need to find some cloud point LiDAR data, which is increasingly available. If it's not available, we found that for spans under 100 meters, those, for the vast majority of those, are basically straight line spans connecting a cut. So you can assume a constant grade if it's a span that's under 100 meters. If it's a span that's over 100 meters, that's more problematic. You're more likely to get a bimodal distribution where you kind of have an upgrade and a downgrade. And so for spans that are longer than 100 meters, you really need to seek out some sort of alternative data source, even if it's just looking at a profile and coming up with your best estimate of an up and then a down. That's still going to be better than just using a DEM for those structures. Fortunately, elevated structures longer than 100 meters aren't that common, so it's reasonable. And I think there was 9 in Vancouver, right? So it's the kind of thing you can go in and do it, but you're going to want to do it because those are going to be important pieces of infrastructure. Okay, so that's on the road grade piece. So now, again, we're still kind of doing the deep dive on data processing, but here's what we've done using the kind of medium-term GPS data results. So speed choice modeling and e-bike speeds. So this was a fun piece. So we wanted to develop a speed choice model so that we can understand this trade-off between energy expenditure and speed of cyclists, and then actually use that in a route choice model. So instead of saying the route choice depends on the number of kilometers that you travel, the route choice is going to depend on the travel time and the energy expenditure. So that's where we're going to be going. But in order to do that, you have to be able to separate the two. So we developed a utility-based speed choice model. It's a utility maximization model, kind of like you know, a mode choice model, something like that. It's not a it's not multinomial, but it's a continuous model, but it's a utility-based model where you have time in there as a pure utility cost. You have energy expenditure in there as a cost, and then you have control of the bicycle as another factor. And you end up with an equation where you can estimate the equilibrium speed, which would be the preferred or desired or cruising speed of the cyclist given a fixed set of environmental conditions. In order to estimate this, you need the physical attributes we talked about before. So you need your rolling resistance and your aerodynamic drag parameters. You also need a couple of physiological variables that represent the human body's ability to convert energy into external power, right? And those are available from the physiology literature, from sports medicine and kinesiology. But what's of more interest to us is the marginal rate of substitution between time and energy. And this is our behavioral parameter. And this is basically the rate at which people would want to trade off time and energy when they're cycling. It's kind of like in transportation, we talk a lot about the value of time in terms of dollars per hour. So that's the marginal rate of substitution between time and money, how much people are willing to trade off a dollar toll for 5 minutes of travel time, right? Reduction. So this is kind of like that conceptually, but now we're looking at the trade-off between time and energy. So if I put in more energy, I save time. If I put in less energy, I could save on energy costs, but I have to expend more time for my trip, right? So that's the key behavioral parameter for the speed choice model. And then, so that's what you need to predict the speed. And in order to calibrate the model, we need observations of an equilibrium speed. So we need people basically observations of people maximizing their utility so that we could estimate this marginal rate of substitution. So we did it with, we estimated it with a basic data set, and we then applied the model to say, well, what happens if you add electric assistance? So if you provide electric assistance such that the relationship between energy expenditure and travel time changes, right? So basically people get free energy if you have an e-motor attached to your bicycle, right? So we said, okay, as you increase the power assistance, and most of the electric bike models provide a proportional power assistance. So if you cycle at 100 watts, then you basically get a multiplication factor where the motor is putting in some factor of how much energy you're putting in. So at 100% power assistance, the motor is doubling your energy expenditure to the bicycle, right? Or your power input to the bike. At 200%, you get triple the power from the bike that you're putting into it. So this was the prediction of how people's energy expenditure would change with electric assistance. So when you provide electric assistance with the motor, the cyclist tends to put in less effort on their side, right? Because they can get the same speed with less effort. They also tend to go faster, which is observationally been seen in a number of studies. So basically, with the introduction of electric motor, cyclists tend to take some of that benefit in terms of reduced energy, and another part of that benefit in terms of reduced travel time. And we did find one paper from Portugal that was reported the speed change and the amount of power assistance, and it supported what we found there. But we wanted to estimate this same model using the GPS data. So in order to do that, we have to identify cruising events in the GPS data. So these equilibrium speeds, right, where a cyclist seems to be going their preferred speed. Here again, this is the non-trivial task, unfortunately. So cruising speed is not necessarily the same thing as an average speed, because people aren't always in a cruising state, right? So when the road grade changes or something happens in the some sort of traffic control comes up, then you have to you have to reach the new equilibrium speed. So not to go too into the weeds here, basically we've looked at a number of different methods of extracting cruising speeds using some fairly complex time series clustering approaches. And we found that, as expected, the cruising speeds were significantly different from the average speeds for the same cyclists. Cruising events were about 15 to 45% of the duration of a trip, depending on the type of trip. And we looked at the cruising speed relationship to road grade, and we saw really high interperson variability, meaning people's preferred cruising speeds, how that changes with road grade varies by person. Okay, so each one of you will slow down a different amount on a hill, for example, right? And so that reflects your unique marginal value of energy expenditure. And we do expect that to vary by person. So again, this kind of supported the hypothesis that we need to try to estimate this for different people. Remember, in this data, we did ask self-reported cycling speeds. And for the most part, people were right. So this is the cruising speed extracted from their GPS data versus people who said they went about average speed, slower than most cyclists, and faster than most cyclists. So for the most part, people who thought they went faster than most cyclists did go faster than most cyclists. And people who thought they didn't. That's kind of interesting. But we're still working on, because we've just gotten to the point where we have a time series clustering approach that we like. We're still working on extracting these marginal rates of substitution for all the cyclists in the data set. And we're going to be looking at inter and intra-person heterogeneity in this marginal rate of substitution. What that means is we expect people's perception of energy expenditure to change depending on the type of trip they're on, depending on the weather, and also depending on some fixed factors like their age, right? So if it's hotter, we imagine the perceived cost of energy expenditure is higher. And if they're going to work, we expect the cost of energy expenditure to be higher than if they're coming home from work and things like that. So still to test on that. And then we will be trying to incorporate that into a route choice model to see if an understanding of the cyclist's perceived energy cost significantly improves route prediction. The other thing we've been doing is looking at e-bikes in the data set. We had about 8% e-bikes, so not a huge e-bike sample. We found that they went about 30% faster just without controlling for anything else on average than the non-electric bicycles. We found that they had not just greater speeds, but also greater speed dynamics. But we also found that they had systematically different sociodemographics and terrain characteristics for their trips, which you would expect, right? So when people talk about e-bikes, we know that the people who adopt e-bikes aren't a random subset of the population or of cyclists. And there's also a lot of hypotheses that e-bikes make it easier to go uphill, so you would expect e-cyclists to be more willing to go up hills, right? So for that reason, we created a matched sample in the general non-electric bike cycling data set, and we matched conventional bike trips to the e-bike trips on 4 dimensions, matched on the age of the cyclists, the gender of the cyclists, the trip purpose, and the terrain type. And terrain was represented by 3 different terrain variables, like average grade, average positive grade, average negative grade. And so we found that when you match the trips, when you match the trip characteristics to the e-bike trip characteristics, there's even a bigger difference between e-bikes and non-e-bikes, right? So the here, I think it's better represented here. So these are representative cycling dynamics for different types of bike groups. So this is the total move distance, then this is the total motive energy. And I say motive energy because that includes the input from the motor and from the cyclists themselves. So I think this is probably the more interesting graph. So here you have the e-bike dynamics created about twice the motive energy of the non-e-bike trips. But the general conventional bicycle pool is this short dashed line here. But once you control for or match based on age, gender, trip purpose, and terrain, you find even less motive energy in those cyclists, right? And so basically what that means is that the difference between e-bikes and regular bikes is even bigger if you compare kind of make an apples to apples comparison versus just the general pool of cyclists. So what we still haven't gotten to yet is using the heart rate data from the GPS survey. We're also going to be doing a similar energy analysis looking at other types of devices besides just e-bikes. And we want to do it with controlled assistance levels so that we can really look at, this one, as you change the power assistance level, look at how well the model predicts changes in speed and energy. So we're going to be doing it, looking at e-scooters and various types of electric assisted mobility devices and validating those with breath measurements as well. We'd like to look at transferability to other cities, especially with the GPS data, because the terrain characteristics in particular vary quite a lot by city. And we are right now using the speed choice model to try to integrate that into bicycle microsimulation as kind of the desired speed for cyclists, which is a key piece of that. So I was supposed to wrap up by 12:15, so I think we're about there. Oh, I went over.
Thank you so much.
Yeah. Thanks.
So we have time for some questions. So if you're joining online, feel free to go ahead and type them in there. And then while those come in, let's start with somebody in the room. Any questions? We'll ask you to just talk into the microphone.
Hi, thank you. That was awesome.
Hi,
I had a question just to clarify. You said cyclist self-reporting is a bit inaccurate versus the data. Was that correct? Or later on, after I'd written that down, you seemed to say that it was more accurate. So I wasn't sure.
Was it here or was it very early?
Earlier than that, that's where I felt I was corrected.
Yeah, so the self-reporting I was concerned about, that was in the INTERCEPT survey, and that was self-reported frequency and speed. And so I will say on the speed, they do seem to have self-reported pretty well. So after getting the GPS data, we were more confident that they self-reported correctly there. But in terms of whether or not they cycle year-round, you know, that's something people always tend to over-report. Now, we don't know whether that over-reporting was consistent between the two groups or different, but it's just a qualifier I wanted to throw out there.
So first, thank you. This is just an excellent presentation. I love the depth of this study. Question about wind speed, both in your specific testing, what did you do about wind speed, but also in your general thinking and modeling?
Yeah.
What do you think about wind speed?
That's a great question. So wind speed is tough because wind speed actually creates the wind creates 6 different types of resistance forces on bicyclists, and we're representing it here as one dimension. And that's definitely a limitation. And the wind direction creates a particular problem. I didn't mention this. I did say that the coast down test, we had 557 successfully estimated out of 620 that took the test. I mentioned braking is one reason they didn't work well. Well, another reason is if the wind angle shifts. So we found in the validation that you need to do it facing into the wind. And the reason is when a cyclist is cycling in general, unless there's a strong tailwind, you have a predominant headwind, which means the yaw angle of the wind, the apparent angle, it seems like the wind is coming from generally this direction. And so you want to do this test into the wind so that that yaw angle, the direction of the wind, is pretty consistent. But as you slow down, if you're running the test and the wind's coming from over here, even if you're going faster than the wind, as you slow down, that apparent yaw angle will shift throughout the test. And that was one of the reasons we think the test failed. In general, we decided to represent it using just this 2 resistance factors as a balance between kind of precision and what we thought would actually get implemented in a transportation model, right? For example, when we're going to apply this to GPS data, we're not going to have 3-dimensional wind vectors throughout the whole city, right? And we didn't have anemometers on all the bicycles because it was based on smartphone GPS data. So our feeling was that given that for the most part it's going to be used in a fairly simple kind of 2 resistance factor framework, it's better to estimate them in that 2 resistance factor framework, but it's definitely a limitation.
Thank you. So Kyle online asks, will you explore bicycle infrastructure type as a parameter similar to grade or a bicycle type that you?
Yeah, so we'll absolutely include that in the route choice models. That's not kind of the main question we have because I feel like that's been done pretty well by other researchers, but because that's such an important factor, you have to absolutely include that. So we'll be including facility type absolutely in the base model and then seeing if energy interacts with that facility type effect. So I don't remember who I was talking to actually. It was kind of in a presentation like this. Someone mentioned to me that they would think people would be willing to expend more energy to cycle faster on a mixed traffic facility since the cars were going faster. And I think that's an interesting hypothesis that I didn't come up with that would be fun to test. So we'll be looking and seeing that. Is your willingness to expend energy to go faster different on different types of facilities?
Hi, Alex. Thanks for all the great R plots too. I like them. So we had I think one of the seminars a couple of weeks ago was somebody from Here Now, and they're doing some like GPS level lane prediction.
Oh.
Have you sort of looked at your GPS traces? Are they going to be able to? I mean, what do you think about trying to predict where which lane the cyclist is using?
Yeah, so we've looked quite a bit at the GPS data, and I mean, even at 1 second, the smartphone-based GPS data we have would not be able to do that with any precision. I will mention on the grade study, besides these kind of fixed data sources, a number of people have mentioned that if you had enough GPS data, you could maybe infer the bridge deck from kind of like crowdsourced if you had literally millions of trips, and I think that's possible. But the lane prediction for every individual trip it seems fairly infeasible with the precision of data that we got from these, but it'd be great if they figure it out.
Great, thank you. Any other questions?
What type of bicycle do you think is optimal based on your studies? Just in terms of weight, for example, or
Okay.
anything else you might want to mention?
Sure. Yeah. So I mean, so my response, maybe a bit snarky, was just going to be whatever the cyclist is most comfortable on. If you're looking to minimize your resistance parameters, then I think there's a lot of information in the bicycling science kind of kinesiology research that does a better job of that than we did, because our goal wasn't to find the most optimal; it was to find the most realistic in terms of what are people actually using. But in general, the types of bikes that people race have less resistance, because that's why they're designed like that. The types of bikes that people race have less resistance than the types of bikes that are more comfortable to ride around on, right? So, you know, thin tires, light, drop position, et cetera, et cetera.
Well, so the question is, it seems to be a couple things are actionable from infrastructure. One is the hills you build with bridges.
Mhm.
Another is the surface, the riding surface. And I wondered if you had any research or thought about both the smoothness of the surface, but also it's the continuity. If you have long, continuous, smooth roadway versus some very rough roadways are slow. So any thoughts on that?
Yeah, that's a great question. We tested different, you'll see someone's on a soft running track there. So we to validate the test, we did it on different surfaces. And as you'd expect, you know, this surface had, I think, 8 times the rolling resistance of paved asphalt, for example. So you can estimate, using this type of approach, you could field estimate different rolling resistance on different types of surfaces. And then once you know, which we still aren't there yet, but once we know the effect of, say, an extra unit of energy expenditure on the attractiveness of the route, and we'll be able to turn that into, say, equivalent minutes, then you'd be able to say different types of surfaces would have this effect compared to percent grade or traffic volume or distance. So I think we'll be able to get there, and we do have methods to actually measure it on real bicycles. And yeah, down the line, hope to get there, because I do think it makes a difference. Although this is just energy, this is not comfort, which is another important factor.
Thank you. Josh online sent in a question. It was noted that e-bike user characteristics were different than the general bicycling population. Can you summarize the demographic characteristic, age and gender differences between e-bike users and general bicycling population? Is it older versus younger, male versus females?
Yeah, we found the same patterns that, again, researchers in the room have found in previous studies, that they tended to be, these were older. They tended to be on hillier terrain. I don't recall if the gender difference was significant or not, but they did tend to be older and on hillier terrain. And I can't recall off the top of my head the trip purpose differences, but send me an email and I could find that data and send it to you.
That sounds great, thank you.
Or
and
Josh,
then,
sorry to Josh.
And then David is asking, did the study include any folding bikes or other bikes with non-standard tire sizes?
Yeah, the INTERCEPT study, we did have a handful of folding bikes. We had e-bikes, and we used the e-bike parameters from this. So e-bikes were significantly heavier, as you'd expect. We had folding bikes, we had tandem bikes, we had some bike share bikes. There was a huge variety of bikes in the INTERCEPT study. You know, 630 some odd bikes. So there is an incredible variety of bikes being ridden out there. They maybe off the top of my head, 50–60% is kind of a standard bike someone would put onto a photo of here's a bike, and then a large proportion didn't fit that mold very well.
All right, I am going to bring this to a close. Before we thank Alex, and I will remind folks in the room, we've got some donuts here if you want to hang out for a few minutes, and then you can ride your bike and burn those calories off. And then I also want to share with everyone that our next Friday transportation seminar is part of PSU's Research Week, which starts, which is next week. So next Friday on May 10th, we're going to have Dr. Correa from Delft University of Technology will be presenting on how autonomous vehicles could shape our cities, research from the Netherlands. And then we're going to have our own Dr. Kelly Clifton and Dr. Chris Monsieur from the College of Engineering and Computer Science lead a discussion with Dr. Correa about the various aspects of autonomous vehicles and their impacts in the future. So we hope to see some of you there, either in person or online. Thank you very much. Thank you.
Thank you.
Thank you so much.
Absolutely. My pleasure.